Many of you know Ian already because he's chair of the Hereford and Worcestershire Earth Heritage Trust. Ian is a geoscientist with broad interest in geochemistry of the Earth's surface, climate change and Earth history. Ian was heavily involved in cave research for 20 years from the mid-90s and published a book with his colleague Andy Baker on the subject. Over to you, Ian, and can you share your screen with us?
Well, good evening, everybody. And it's a pleasure to be talking to the Black Country Geological Society and other friends who are listening in this evening. This talk is called Atmospheric Cave Science. It's about what we discovered about how air moves in caves and what affects its composition. But it's also about how do we do some simple studies on how material moves around and how it accumulates, the subject we call mass balance. And I shall apply it to the atmosphere of the Earth and our rising CO2 in the Earth. And I'll also mention a bit about COVID issues and the effect of stagnant air on COVID transmission near the end of the talk. So in this picture that you can see here, there's a caver, quite a famous one actually, a cave scientist, and he has created some smoke in the cave by nefarious means. And this allows the movement of air to be examined. Inside caves, you don't normally have a strong draft. You normally have very, very gentle air currents that are very difficult to pick up. And this smoke method actually is a very good way of working out what's going on. So we'll be having a look at that as one of the things this evening. Now, I talked to the Black Country Geological Society last time was in 2014, actually. I've lectured about 3 times previously. 2014 was the last time. And I had a talk then mainly on how stalagmites can be used to find out about past environments and climates. And in that talk, I had a short section on how do caves work. And here I expand a section of that topic to look at cave air. So the first thing I'm going to do is to make an analogy between a cave and a person and a planet using the concept of physiology. So a cave has a physiology. It acts as a system, and as part of that, it maintains a constant temperature, homeostasis, and CO2 is travels around the system. It increases and decreases by different processes within a cave. And if you think about a person has a physiology acting as a system. We maintain a constant temperature. We certainly exhale CO2. And the same, of course, applies on the planetary scale. Our constant temperature has been maintained through geological time, more or less constant. And of course, CO2 is one of the big issues of the day. So there are interesting parallels that one can make on different scales. So I'm going to be talking about carbon dioxide quite a lot. So let's see how it links to a cave environment. We've got a cartoon here that shows us a soil zone overlying a limestone terrain that has been karstified. That is, it's been dissolved, and we've had various different channels and caves have developed inside it. Now in the soil zone, there's a lot of carbon dioxide. You wouldn't be able to breathe soil air. It's too rich in carbon dioxide. And that carbon dioxide dissolves in water to form carbonic acid, which attacks the limestone and makes it dissolve more effectively than if the water was pure and didn't have any carbon dioxide in it. It causes dissolution, and we get ions, calcium ions and bicarbonate ions dissolved in the water, which then pass through the system. What happens when that water reaches a cave is that it encounters an air which has normally got a lot less carbon dioxide in than the soil had. And that means the water is unstable and it releases carbon dioxide to the air. It degasses carbon dioxide to the air, and that promotes the precipitation of calcium carbonate, which of course we see as stalagmites, stalactites and flowstones in caves. So carbon dioxide is very much part and parcel of the system of caves and the way that, stalagmites form. Now, why should the carbon dioxide in cave air be lower than in the soil? Well, it's often still higher than the atmosphere outside, but it all depends on the rate at which the air is moved around in the cave system. It's clearly being built up by exhaling from the water that drips down from the soil, but it will also exchange with the external atmosphere, and that keeps the CO2 level down, at least in caves that have some clear connection with the outside. That does happen. But occasionally in cave passages, you have more stagnant air, which of course will be dangerous for cavers. Now, my work in caves first started in 1994 in this atmospheric region here, in Trentino region of northern Italy. And over the years, together with my collaborators Silvia Frisia and Andrea Bazzato, we tried out many things for the first time in cave systems when applied to looking at cave environments and the stalagmites that form there. And for a period of 20 years, the little cave there was intensively studied. And we also looked at stalagmites and stalactites that had annual layering in them, and did a lot of things for the first time. And work is continuing now because I'm on the Anthropocene working group, which is trying to come up with a definition of an Anthropocene epoch as the latest epoch of geological time, later than the Holocene. And as part of that process, a series of type sites are being studied intensively. And the cave one is this one. It's Ernesto Cave. And Sylvia and Andrea are doing some more work adding to our body of data that we have on this site. So it will become better known again when that work is finished. So this cave we see here in the Trentino province is at 1,100 meters altitude and only has a mean temperature of 6 degrees because it gets very cold. There's very thick snow in winter. But as you see, it's a wooded catchment. And if we look at the cross section through the cave, we can see it's really quite small. It's only about 50 meters long, a few meters high. You can stand up and walk through it easily enough. It was for a long time sealed off. And then in the 1980s, a little boy called Ernesto was the only one small enough to wriggle into this space where people suspected there might be a cave. And so they named the cave after him. Interestingly, then, the cave was occupied by humans thousands of years ago, but it was sealed by this debris moving down the slope outside the cave. And one of the things that we've done is to kind of reconstruct what's happened over the past 10,000 years. And there's an interesting observation here. There's a skull of a cave bear. It's got charcoal on it, and that's from a fire. So there were people making fire in the cave, and that was about 9,000 years ago. But then that seemed to stop. And this is when we think the cave has been sealed off. And then after that, there's a record of what's going on in terms of deforestation later on. And then it's only the 1980s that the cave actually opens up again. So it's a small site, and it's a beautiful experimental site because it's reasonably well contained, and the water doesn't travel very far to get into it, and the whole system is really nice and neat. And so we've used it also for the studies of cave air. Now, one of the observations that you can make about this cave is that it's strongly seasonal in its characteristics. The external temperature is strongly seasonal. That's what you see as the purple line here. So we can see this is ranging from, in the summer, temperatures in the teens down to below zero in the winter. So it's a very strong temperature driver. and that affects the amount of carbon dioxide that is released into the soil by decomposition of organic matter and plant respiration. So the fluxes of CO2 vary quite a lot through the year. But what we also find is that the amount of CO2 in the cave air also varies a lot between summer and winter. And in the summer, we can see it's up to values of about 1,500 parts per million, whereas in the winter, it's down at 400 parts per million or below. And that's pretty close to the composition of the external air. So CO2 builds up a lot for much of the year, but in the depths of winter, it drops right back down. Now, what is controlling that? How can it drop so low? This is what we can explore. Now, a consequence of that changing amount of CO2 in the air is that the growth of stalactites and stalagmites changes seasonally. And it's shown most beautifully with these examples of soda straw stalactites. So soda straw stalactites are simple hollow tubes that form around drops of water. And if we look at this, and they're quite fragile, and here we're looking at a cross section through one, and you can see it's got this very, very clearly marked banding in it. And each band represents a thicker zone where the calcium carbonate was growing more rapidly during the winter. So this was a great discovery that that there's this rhythm, this annual rhythm that is imprinted on the stalagmites and stalactites in the caves. And obviously, I talked about that actually last time I came to the Black Country Society. But for now, I'm just going to go back to talking about the cave air. So the cave air then is doing this. This is this graph, the third one down. But the pressure of carbon dioxide in the soil is also varying, and it's varying more extremely, and it's going up to values of well over 10,000 parts per million. That's more than 1% carbon dioxide in the air in the summer, and then dropping right down in the winter. So this variation in the cave, is that due to something directly to what's going on in the soil, or is it something to do with the air is circulating, or is it a combination of the both? One of the things you can do by way of an experiment to work out what's going on is just to study the impact of visitors. Now, this cave's in quite a remote place, and it doesn't get very many visitors, so it's only a few times each summer that people come in. But because there aren't very many visitors, a lot is known about them. We know exactly how many they are, whether they're adults or children, and how long they stay there. And this is the impact they have. So here so the number of cave visits, the number of person hours is shown by the red bars that are at the bottom there. And then the change in the pressure of CO2 in the air, that's shown by the blue lines. So every time there's a substantial visit, the CO2 goes up and then it gradually declines. But this gradual decline is towards values that were there before the visitors came in. But as you see, it takes some time before you get back to those levels again. And that's telling us something about the air exchange time of the cave. Now, to look at this a bit more, we can do some arithmetic, and this involves doing something called systems analysis. And this was something that geographers got fascinated with back in the 1960s. And this guy, Dick Chorley, was an early adopter, and this was how other people saw him at that time. But these systems are represented by what are called box models, which are used routinely by environmental scientists these days. And I'll just show you a simple example about how they work. Now, I devised this way of explaining how these things work for my inaugural lecture that I gave at Keele University. And you can look at the cars in the car park and tell me what year that was. Well, it was 1994. So I'm going to tell you then a story about a supermarket that's going to tell you about how systems work and how we can use them. So I'm using as an analogy the number of people in a supermarket, and I'm comparing that with the amount of carbon dioxide you have in a cave or in an office or in the external atmosphere of the Earth. We're just using it as an analogy. They're similar things. So in this case, we're looking at what controls how many people are in a supermarket. Like, what controls the amount of CO2 in air? How many people are in this supermarket? Well, clearly, it will depend on how many people are arriving in the supermarket. That's an important control. And I'm saying for this example that every minute, 2 people are coming into this supermarket. Now, I must stress here that this is a well-run supermarket, it's a well-ordered supermarket, and everything is very much in balance. So this means then that 2 people are leaving the supermarket every minute as well. 2 people coming in, 2 people leaving. Everything is in order. So, and if we do the analogy with the amount of CO2 in the atmosphere, you can say, well, this time when there's not very many people coming in and not many people going out, that's a bit like carbon dioxide in the atmosphere before the Industrial Revolution, before it started to build up. Now we can then examine what these people are doing inside the supermarket, and we can observe that in this particular supermarket, there are 60 people shopping at any one time. And what we can do then is to work out something called the residence time. How long do they stay shopping? And if there are 60 people there and 2 people are entering and 2 people leaving, that means 2 people must also be going to the tills every minute as well. Then 60 divided by 2 is 30 minutes, and that's how long they are staying shopping. And then we look at the tills and we see there are 8 tills open in this supermarket, and there are and 16 people are queuing and packing. So there's a 1 in front policy at this supermarket, 16 people queuing and packing, and 2 people are leaving the tills every minute. So they're spending 8 minutes at the till in this particular supermarket. Everything is ordered, everything's like this, and we can work out these residence times for shopping and a residence time for queuing and packing. So we've got 2 different, what we call reservoirs. So if you think of CO2, this reservoir could be the atmosphere and this reservoir could be the oceans, for example. So we can, it's just an analogy. Now then, we can express, if any of you like mathematics, you can just write a simple equation for this and say, well, the number of people that are going from one place to another, let's say going from shopping to the tills, that's equal to the number of people in 1, which is called mass 1 here. And if you multiply that by some kind of rate constant, then that tells you the flux, which is the number of people moving from the main part of the supermarket to the tills. And this rate constant is actually the inverse of the residence time. So whereas the residence time is 30 minutes, that rate constant is 1 over 30. So m, the number of people, that's 60, times the rate constant, which is 1 over 30, is going to give us 2, which is the number of people that go into the tills at this point. So that's expressed in mathematics for those of you that are interested in that. But you can just think of it intuitively as well. Now, and then the people leaving the supermarket, they then go out to a reservoir outside the supermarket, which is the car park, and that's what we might call reservoir 3. So we can just have a look and solve this. So in this case, the K23 would be, the rate constant will be 1 over 8 because the residence time is 8 minutes. Now, the thing about this, what now gets good is that if we now change the system, what happens if we now have a situation where the store gets busier and 5 people start entering per minute rather than 2? What goes on? Well, we can use these equations to basically solve what should happen in that steady state. So there we are, we can see the car park's full, 5 people are entering the supermarket any minute, everything is getting busier. Now, because this is an incredibly well-run supermarket, it actually stays just as efficient when it's busy as when it's quiet. Now, you may or may not believe that, but for the purposes of the mathematics, let's keep it simple, and that's what's happening. Now, how many people will be in the store shopping? There are now 2.5 times more people entering and leaving the supermarket. How many more times people are shopping? And the answer, and maybe intuitively you might get the idea, it's 2.5 times more people are shopping, and there are 2.5 times more people at the tills. But the great thing is that because it's a well-run supermarket, they've opened more tills, and that keeps everything in steady state. So this is something that is a system that automatically regulates itself. And as we'll see in a moment, when we do an experiment in my office, you can have a system that is self-regulating, even if it has no moving parts, as I'll explain in a moment. So this is an example of a system. Systems are all around us. This is the way the natural world and a lot of human parts of the human world work. Now, and we can now see what would happen if 5 people started coming in per minute. What would happen is that the number in the store would rise up, and then it would gradually flatten off at a level at 150 people in the store. That's 2.5 times more people than were there before, and the rate at which people are leaving per minute, that also rises until that reaches 5 per minute going out in this case. So the system responds quite nicely in that way. So that's that's an example of people shopping. Let's now transfer that to the Earth and its CO2 in the atmosphere. And this is the amount of carbon in different reservoirs, different boxes, if you like, in the Earth before the Industrial Revolution. There were 600 gigatons of carbon in the atmosphere at that time. Now, it's increased quite a bit since then. Why has that happened? Well, a key thing is the burning of fossil fuels and deforestation. That's introduced an extra supply of carbon in addition to the way that carbon was being cycled between these different reservoirs before that. And the knock-on effect of introducing this extra carbon is that, of course, the amount in the atmosphere rises. It's gone from 600 to 750 gigatons. And also, the amount that is being lost from the atmosphere and taken up in growth of plants is gone up from 100 to 102. That's a fertilization effect. So plant growth is increasing. But also we see that there is more taken up in the parts of the ocean which are colder and in which CO2 can dissolve, whereas parts of the ocean that are warmer, they tend to release CO2 more. So the fluxes of CO2 into the ocean and out of the ocean have gone up quite a lot, from the mid 70s up to 90 or so. And there's a bit of an imbalance. We see there's this extra CO2 that's been brought in. Some of it's accumulating in the atmosphere. Some of it's going to enhance the growth of plants on land, and some of it is adding to carbon in the oceans and actually acidifying the oceans. So there's a lot going. So the Earth system then is resisting the rise in CO2 in the atmosphere, but it's still going up. So that's an example of how we apply these kind of box models to this sort of global state. Now let's think about it in terms of a room or a cave, and let's think about people as the agents of introducing CO2. Now, when I gave another inaugural lecture, this time was in Birmingham in the early 2000s, and because that was in pre-COVID days, I was able to bring along a little instrument which measures the amount of CO2 in the air. And we had it logging during the lecture, and you could actually see the level of CO2 in the air going up because of all the breathing that was going on. And I also had fun by asking a pro-vice chancellor, who was known for liking a drink, to blow into a bag during the lecture. And what I did, of course, was rather than breathalyze him, I was just measuring the amount of carbon dioxide in his exhaled breath. And it's quite large, actually. Whereas in the atmosphere, the percentage of CO2 is, well, it's 0.04 now, around 0.03. The amount that you breathe out is 100 times greater. It's 3.6% carbon dioxide in what you exhale. So if you snuggle under the bedclothes at night and don't get any fresh air, you'll be breathing, you'll be feeling a bit odd because the amount of CO2 rises very high. And if your teenage relatives want to have a sleepover, make sure they keep the window open. That's the idea. Anyway, we can observe this directly, and I did it in my office in Birmingham at that time. And I did some simple calculations, and I said, well, this is my breath. It should have 3.6% CO2. I looked up the medical textbooks. I should be breathing 15 to 18 breaths a minute, and I should be exchanging half a litre of air every breath. And therefore, every minute, I should be exhaling about 8 litres of air, and that's got 3.6% CO2 in it. Then, if you know the volume of the office, 32,000 litres in my case, standard size office, and then therefore it should take, if it's 8 litres per minute, it should take 4,000 minutes to exhale the volume of my office. And therefore the rate of addition of carbon dioxide is 36,000 divided by 4,000. That's 9 parts per million per minute. So if we start off at somewhere around 400 or just below, every minute it should be rising by 9 parts per million. If it's not, if the office is not ventilated, so you get some idea about how quickly it would build up. So I started the experiment by going out of the room for a while, having the window open so that the air inside the room was the same as that outside. And at that time, it was 380 parts per million. And then I just left I just came back into my office, shut the window, sat at my desk. Nobody bothered me for 3 hours. And what happened was the CO2 in the office went up like this. So it rose pretty steeply, and then it flattens off. Now, that's exactly the same pattern that we saw in the supermarket. When there were more people coming into the supermarket, the number of people in the supermarket kind of rose quite quickly, and then it flattened off towards a new steady state. And in this case, if you were to use the 9 litres a minute breathing, which the textbooks tell me, it doesn't actually fit the observations. But if you change the model, so that's 7 litres a minute, so I must have been breathing a little bit less than the textbooks say I should, must have been very calm, then it actually fits the observations really very, very well. Now, the reason that it's flattening off is because the system is responding to the increase in CO2. My office is not hermetically sealed. If it was, the CO2 will be going up as a straight line. No, it's ventilated. And as the amount of CO2 in the air increases, the small exchange of air between the office and the outside becomes more and more efficient at removing CO2. So there's no moving parts on the ventilation. It's just a small ventilation grill, which I hadn't even noticed. I hadn't noticed it was there until I went to look after this experiment. There is a small ventilation grill. It gets more efficient as CO2 rises in the room. So that was interesting and also salutary, because these sort of levels of 900 parts per million CO2 are levels that are predicted to be what the whole Earth's atmosphere would be like if we carried on with our civilization as it is at the moment, emitting the amounts of CO2 that we do now. That's what will happen to the whole planet in a few decades' time if we don't do something to control CO2 emissions. Well, when it comes to the medical side of things, generally speaking, it's thought to be a good idea to keep carbon dioxide in rooms below about 1,000 ppm. You don't really notice it at that level, but actually your physiology starts to be affected. European standards, we can say, limit it to 3,500. And once we get up to more 1,000 ppm than that, then it really starts to affect people's capability of concentrating and doing work. And this has become a matter of concern when it comes to classrooms, schoolrooms. If they're crowded and poorly ventilated, then that's an issue. People actually can't concentrate so well, and so poorly ventilated spaces are bad news even before COVID. And this was the title of an article in The Guardian in 2019. Air pollution rots our brains. Is that why we don't do anything about it? So I just mentioned then that the CO2 emissions, if the worst scenario happened and CO2 emissions carried on going up like this, then the amount of CO2 in the atmosphere by the year 2100 would be around between 900 and 1000 ppm. Now, we do hope that it won't be like that, that instead we'll be able to control our emissions in something like the red dashed line here, perhaps, and keep the CO2 levels down. But this can be, as you've heard all the COVID scientists say, they can model this. And using something simple like those box models I've just shown you actually gives you the main approach to the answer. Now, we applied something like this sort of box modeling to this cave in Italy. And so there's the cave. It's got a certain volume, it's got a certain concentration of carbon dioxide. And what happens is that CO2 comes in from the soil. That's what we call flux 1. It's released from drip water, dripping into the cave. When visitors come, they release some CO2 as well. And then the cave must ventilate to the external atmosphere. Now, it's not entirely clear how it does that, because most of the time the cave is closed by a door, but there must be small cracks connecting the cave with the external atmosphere. Otherwise, the CO2 concentrations will be very high and they wouldn't go down very quickly when visitors have been there. But there must be cracks that we can't detect. So one can set up a set of simple equations like this to work out what's going on in this cave. And you can use the behavior of visitors to help calibrate it. So there's the visitors coming in, CO2 comes up and it drops down, and it declines exponentially. And once it's dropped down to 1 over 2.7, 1 over E of its original value, that's what's called the air exchange time. So here we can see it's about 2 days in that case, in air exchange time. Now, something dramatic happens between the summer condition and the winter condition. You can see how CO2 drops right down. And we were really interested to find out why that was. But the problem is that by the time you get to November, nobody wants to go near the cave, except the scientist researcher. So my colleague Andrea was wanting to try and work out what the air exchange was in winter. So we had the bright idea of letting off a CO2 cylinder in the cave. And so, well, he volunteered to go in and do the experiment, and I did the calculation as to how much the CO2 in the cave would rise when he let the cylinder off. So I had to get that calculation right, and it was fine. So he went through the cave, adding CO2 fairly uniformly throughout the cave volume and creating an artificial spike. And what we found was that in that experiment, the air exchange time was now 0.4 days, less than half a day, whereas in summer it was more like 1.5 days. So that actually showed us directly that the air exchange was faster in the winter. And it wasn't just a matter that there was less CO2 coming in from the soil. The air exchange was actually faster as well. So that was quite a good result to have. And we were then able to solve all these equations and work out what was going on. Now, something else that happens in caves is the release of radon. And if you're a cave guide, you have to wear a badge, and radon is monitored. Well, you have to wear a badge if it's a cave where there is a significant issue with radon. The map shows us the parts of the country where the radon emissions are higher. It's basically where the rock underground contains uranium, and so it could be a granite or it could be a potassium-rich clay mineral releasing the radon gas. Now, the radon decays in a few days to another radioactive species that attaches to dust, and that be breathed in, and that's the problem. And we can see here this is a problem in houses, and so sometimes houses have to have additional ventilation to stop radon building up inside them. Now, radon's great as a tracer because it's not created in the soil. It's great as a tracer to work out about air ventilation in caves. And so this is an example from a cave in the Czech Republic where they've done a lot of work of this sort. And these are a whole series of years from 1985 to 1995. And here we see the outside temperature going up and down each year. And the amount of radon in the cave goes up and down more or less perfectly with that. And that's that change in the radon concentration is simply due to this faster air exchange. So if you're measuring radon, you can work out the air exchange and the circulation directly. Now, sort of stepping back a little bit to think of caves more generally and what controls the way that air circulates in them. One thing is the geometry of the system. Is it a simple tube? Are there lots of tubes connected together? And a typical cave has got such a complicated shape that it's almost impossible to actually write an equation to solve how it should circulate. You just have to observe it and see how it does. But one important principle when looking at cave air circulation is that the density of the air is a fundamental control on what goes on. So here we're plotting the density of air against the temperature. We can see that as the temperature increases, the density of air goes down, as you might expect, but also that the air pressure has an effect. This is a low pressure, 980 millibars, and there's a high pressure, over 1,000. And then there are differences between dry air and air that's saturated with water, and also air with more CO2 in. These are all different things. So in principle, air can, the density of air controls the way in which it circulates. Now, there is a myth about caves, and that is that because carbon dioxide is a heavy gas, that therefore you get sort of carbon dioxide pools in caves. And that's not actually the case. Sometimes you do get a stratification of air in caves, and the air that doesn't move tends to be richer in CO2, but it's not sort of sitting there at a lower level because it's rich in CO2. It's because of the way that the air is circulating anyway. Anyway, so density is an important control, and we can see that it actually has an effect in several of these examples that I've drawn here in these cartoons. These are 5 different ways in which systems of air circulation, what's called cave breathing, wind forcing, where wind is pushing into a cave, chimney circulation, seasonal changes in external air temperature, giving rise to convection effects, and then stream flow. Well, stream flow and wind forcing are not to do with air density, they're to do with movement of fluids under forces, but the others are illustrations of the role of density. Firstly, I'll just say something about these amazing caves here in the Nullarbor Plain in Western Australia. This is a flat plain bordering the Southern Ocean in the west of Australia, and it's a kind of featureless landscape, and it's got these holes in where over a long period of time tertiary limestones have been dissolved, and the caves are formed, and the roofs are locally collapsed, and animals fall into here and die, unfortunately, in very large numbers. And so brave cavellers go in and try and avoid the snakes that have fallen in. And what happens here is that this small entrance is the site of air circulating in and out, and changing quite dramatically in response to heating and cooling effects, changing the air density and therefore the pressure. So you can actually have winds of several meters per second blowing in and out of these holes at different times of the day. So that's a kind of like an extreme example of air movement. But something much more gentle is shown by this cave. This is quite a famous cave called the Glowworm Cave in in New Zealand, where there are glowworms on some of the passages. And this is a cave that has an example of chimney circulation, a circulation that reverses. So in summer, the air in the cave enters in the upper entrance and cools down and flows downwards. Whereas in the winter, the air tends to warm up in the cave and flow upwards. So there is a reversing circulation between summer and winter. Some caves actually reverse even between day and night, but this is between summer and winter. And here's another example of a summer-winter alternation. This is a cave that we've worked in Austria called Obia Cave. And here we see a kind of fog outside the cave entrance. And this is where air in summer is coming out of the cave by this system you can see here. And as it comes out, it cools warm air outside and causes moisture in that warm air to condense. So this is one way that people find cave entrances, actually, is by looking out for strange fog in summer near some of these caves. And so we were able to work out from this some extraordinary differences between different caves' behavior. So here I've plotted the volume of the cave, everything from 1,000, 10,000, 100,000, a million cubic meters, and then the air exchange time. How long does it take for that air to refresh itself? And we've looked at the Ernesto cave, and the minimum air exchange time is 0.4 days, what we saw just now, but it's a tiny cave. It's only 1,000 cubic meters. And what's extraordinary is that Carlsbad caverns, which are this enormous system that are several thousand times bigger than Ernesto in volume, nevertheless can have air exchange times a little more than a day or two. And that just shows that there are many, must be many entrances and must be many ways in which the air can move in that Carlsbad cavern system. And the Obia cave I showed you just now, that's quite a small cave again, but its minimum air exchange time is in winter is very short indeed. It's only 100th of a day, and that is a very dynamically circulating cave indeed. And here's another example. I don't know how many of you have been to Gibraltar, extraordinary place. The rock Gibraltar here, it's riddled with holes. It's got a lot of natural caves in them. We can see here people inside one, but it's also got some artificial tunnels that have been dug through during its long military history. And there's a tunnel in the middle called the Fossway, going right through the middle of the rock, and that has clearly modified the natural pattern of circulation of air in this system. In the winter, what is called ground air, the air inside the rock, tends to move up, but in summer it tends to move down. But the effect of having this Fossway thing there is to concentrate the flow around that particular site, and that's been established by a whole raft of monitoring work by Dave Matty from Royal Holloway and Tim Atkinson and colleagues. So that's quite a remarkable thing, and that almost certainly is having quite a big impact on the way that the stalagmites are growing in that particular site. So people are very interested in that site because over a long period of time, the rock has been uplifting, and the environments where stalagmites are growing are emerging from the sea over time. So it's a very dynamic place if one looks at it on a long time scale. Well, another thing that was discovered in this cave in Gibraltar is that methane was being removed from the air in the cave. So methane goes in the cave, but no methane comes out. So what's happening is that the cave is acting as a sink for methane, because methane is being oxidized in caves by bacteria that are called methanotrophs, which are creating carbon dioxide from the methane. So it actually acts as a sink for methane, which is great. And so when Dave Matty discovered this in 2012, it was the first time people had really realized that this could happen. And it may be quite an important way in which methane is removed from the atmosphere globally. Now, I'm going to take you to Australia. I'm going to leave off the equations for a bit and just show you some examples of some nice caves in Australia. where there is an issue with carbon dioxide in some of them. And we're down here in the southwest, Western Australia, a really beautiful part of the world, these wonderful eucalypt and tall cherry tree forests. And we're looking out of the Golgotha cave entrance here up at the forest outside. And these caves are also subject to periodic fires. And then we've done a lot of monitoring of the elements that are taken up as nutrients by the trees. And we can actually observe in the drip water chemistry how the nutrients are being taken up and are reduced in concentration in the drip water as the forest recovers after a fire. And there's a lovely picture showing you the vegetation that springs up once you've had a fire. So that's some of the work that we've been doing there is related to those issues. But I just want to show you a bit more of a cook's tour of a particular cave where CO2 is a problem. Oh, sorry, this is just a picture of an arum lily, and I saw this and I thought this was really nice and went back up to Golgotha Cave to say to the warden there that I'd seen this lovely plant, and she said, "Did you kill it?" Because of course it's an invasive species from South Africa and they didn't want it there at all. Right, so we're now going to go to Ngilgi Cave over here near Yangalop and have a look at what the issues are in this cave. Now it's really beautiful, it's really small, and you get quite a lot of visitors there, and you just kind of go around a circuit in the main part of the cave. It's richly decorated. And they also offer adventure caving, where, as it says here, don a hard hat and head torch for an incredible adventure tour, crawling, climbing and squeezing through the depths of Ngilgi Cave. So, and children aged 10 and older are able to do this. So, now we were there in the winter, and we went on this deeper part of the cave, and we talked to them about carbon dioxide, and we measured carbon dioxide. And the conclusion was that they should not be taking tours in the depths of the cave in the summer. So anyway, we are down here in the deep part. This is the thing they call the pinch gut, which, as you can imagine, was a bit of a problem for me. And there's some beautiful things there, these extra long soda straw stalactites. And this extraordinary thing, it's a sand bed, so water runs into it. And the water dripping down flows over the surface of this spiditherm that's formed this kind of fan shape, and then the water sinks into the sand. And then they have little pools and these beautiful crystals growing in the pools. So it's really very nice and a great experience for visitors to go down into this part of the cave. It's a very intimate part of the cave. You're just squeezing through these different places and through the crystal crawl into the potbelly chamber. And there's the potbelly column. Oh, it's a stalagmite, and lots more stalagmites in the potbelly chamber. And then something really weird. What on earth is this? And in fact, this looks like some kind of monster from the deep. And it's a stalagmite that has been overgrown with plant roots. And these plant roots have come out of the floor. That's what's happening here. They're coming out of cracks in the rock. They're coming out of the floor of the cave. They're seeking water and they're growing luxuriantly. They look like triffids. So quite an extraordinary sight. Now, this is how we measure carbon dioxide. This is using a detector. It uses infrared to detect carbon dioxide. And that's actually why carbon dioxide is a greenhouse gas, by the way, is because it absorbs infrared radiation that comes from the Earth and retains heat in the atmosphere. So the same principle is used for this meter to measure carbon dioxide. Now, in the show cave, this Ngilgi show cave, in the spring, CO2 is 6,000 ppm. That's pretty high. It's higher in the summer, and it's much higher in the lower passage too. So you can see that that lower passage is potentially an environmental problem. Now, there's something else going on here, and that is the visitors. So what happens with visitors? So if we look here, this is looking through from the end of August through to late September in 2008. And this is the CO2 level in the morning, and this is the CO2 level in the afternoon. So you can see that they tend to be higher during the afternoon. There's also a weak relationship between the number of visitors daily and how much the CO2 has risen during the day. So visitors do have an impact. They do raise the CO2 level, but then it drops back down again overnight. Now, there are 60,000 visitors annually, and we were there in spring, 3 times as many probably in summer. So that would cause a significantly higher rise in CO2. Now, why is CO2 so high in this cave? It is pretty high. Is it the visitors? Well, the number of visitors is not huge, although the cave is relatively small. Are the visitors the problem? Well, the cave management thought, well, the CO2 level is a bit high here. So let's solve the problem, shall we? And to solve the problem, what we'll do is to pump the air out of the cave. And that'll be a great idea. So that's what they did. And the problem got much worse. And being Australia, this is their approach to this. This is how they would view the situation. So here we got the problem-solving flowchart. So we've sucked air out of the cave. Does the bloody thing work? Yes or no? No. Oh. Did you stuff around with it? Well, yes. You bloody idiot. Does anybody else know? Yes. You poor bastard. Can you blame somebody else? So you can see the whole thing. That's the Aussie approach to it all. So it was the wrong solution to suck air out. The cave actually must be quite strongly ventilating because the effect of visitors is removed by the following morning. So the air exchange time must be only about 12 hours or so. And I calculated that several million litres of air are exchanged every day. So it's actually quite a dynamic cave. So the problem isn't so much the visitors, it's more that the CO2 coming into the cave by natural processes is quite enormous. And this is this thing that I mentioned in Gibraltar, we call ground air. There are all the plants' roots that are respiring, and you saw the plant roots growing up in that triffid kind of thing, and that's putting a lot of extra CO2 into the air, and that will be more abundant in summer when conditions are drier and the ventilation could be weaker. So that's the nature of the problem. So the solution here, what should the cave management have done? Well, rather than suck air out, they should have blown air in. If you blow in air with low CO2 into the cave, that would have been a better solution. I think that's what they are now doing. And then finally, a couple of slides about COVID. And it was, if you go to this particular government website, they advise you about ventilation and air conditioning. And there's a whole series of sections about why ventilation is important and so on, and the issues that arise from it. And there's even a little video, the importance of ventilation to reduce the spread of COVID-19. So, as Catherine Notes says, when a room doesn't have any fresh air, where people are generating large amounts of aerosols through singing and loud speech, that's when transmission of coronavirus is most likely. So you need this fresh air from outside. Now, it turns out that actually that carbon dioxide is a very good proxy for the quality of the air circulation. The carbon dioxide level, the higher it is, the worse the ventilation in a site. It's quite an easy thing to measure, and it's a very good indicator of whether a room is healthy, both in relation to CO2, but also in relation to COVID transmission. And there's a study that was done by the University of Cambridge on air circulation. And although I've shown you some quite simple systems, I mean, they published their results in the Journal of Fluid Mechanics. So you can imagine their mathematics was somewhat more high powered than mine. But here we've got an example of a bad ventilation. Many ventilation systems are designed to keep the conditions uniform within a room. and they sometimes introduce barriers and to encourage mixing, and that's actually a problem. Whereas good ventilation is displacement ventilation. Air is introduced at a low level and leaves at a high level, and it simply moves through the system, doesn't mix excessively, and that reduces the environmental hazard. It reduces the virus load, reduces CO2 quite effectively. So, and that is where I will finish. Thank you very much indeed.
Thank you, Ian. That was splendid. It took us into realms for me that were very new.